Back in the February video, I teased building an obstacle avoiding robot using relays. I was originally going to do this section in that video, but I figured I needed to rein in the tangent that I was on, and as EdgeEffect said on that video, I was already on one hell of a digression. So today, we're going to build an obstacle avoiding robot that will clumsily meander around your room. But before getting into that, I wanted to give an update on the Bare Metal 386 series. Don't worry, I'm still working on it. But at the end of the last video, I promised that we'd be using Ghidra to do the BIOS disassembly. And while loading the BIOS image into Ghidra was fairly straightforward, the analysis process was far less automated than I thought it might be. While you can view the disassembly, it doesn't seem to do any sort of data flow analysis in an automated fashion. So I fell down a rabbit hole dusting off an emulator I'd written for this board before any of this had happened. So if you want to check that out before the next video goes up, the GitHub page is on the screen, and the link should be github.com/technoman117/tsx86 emulator, and the link will be in the description down below. So to start, I need to introduce a new component, which is this limit switch. Unlike the push buttons we were using previously, these are like the contacts in our relays. They are double throw switches. When the switch is pressed, the contacts are connected one way, and when the switch is not pressed, the contacts are connected the other way. So if we're only using 2 of the 3 pins, it means we can configure these switches as either normally closed or normally open switches. And to show this, if we put some LEDs in our breadboard and connect them through some resistors and then our switches, you can see that for the normally closed switch, which I've chosen to represent with green wires, when we press the switch, the light turns off, and when we release the switch, the light turns back on. And for the normally open switch, which is designated by these red wires, the LED turns on when the switch is pressed and turns off when the switch is released. And the reason that this is important is if you remember the latch circuit from the previous video, it took 2 relays. One to invert the state of our normally open push button to supply power to the coil of the second relay which formed the latch. With the normally closed switch, we can actually simplify the latch circuit to just a single relay. Rather than using an inverter to supply power to the coil of the latch relay, we can just use a normally closed switch. When the normally open switch is pressed, the relay will turn on, and when the normally closed switch is pressed, power to the coil will be interrupted and the latch will turn off. Moving over to the breadboard, let's build one of the single relay latches to serve as a push-on, push-off power switch for our robot. Starting with the relay, we'll connect the negative side of the coil to one of the relay's poles, and then the normally open side of that pole to ground. This forms the path to ground for the coil when the latch is triggered. Next, we're going to connect the other pole of the relay to the positive rail of the breadboard, then the normally open side of that pole to the positive side of the power input, and then the negative side of the power input will go to the ground rail. When the relay closes, power will then be supplied to the breadboard. We'll then hook up an LED to the positive rail, a resistor to the negative rail, and connect the other side of the LED to the resistor to show us when the power is on. Next, we'll connect the positive side of the power input through our normally closed switch into the positive side of the relay's coil. This will supply power when the switch is not pressed, meaning it will serve as the off button, as power will be interrupted when it's pressed. And finally, we'll connect the negative side of the relay's coil through our normally open switch to ground. When the switch is pressed, the circuit through the relay's coil will be completed, turning it on, meaning that this serves as our on button. And now if we connect power to the circuit, pressing the red button will turn the circuit on, lighting up our LED, and pressing the green button will turn the circuit off. And at this point I realize that the colors are logically backwards. Most power tools use green to indicate turn on, and red to indicate turn off. Oh well. We now need to talk about the other types of logic gates. In the last video we talked about the NOT, and OR gates, but what about the other primitive gate types, such as the NAND gate, the NOR gate, and the XOR gate? We could form the NAND and NOR gates by inverting the output of the AND and the OR gates, but that would take 3 relays per function. And if we look at the simplified diagrams of these logic functions, they can be implemented with only 2 relays. So how does this simplification work? To answer this, we need to take a look at the laws of Boolean algebra. Each of these laws will have an AND form and an OR form. The first law is called the identity law. It states that anything ANDed with 1 is itself, and that anything ORed with 0 is also itself. Next we have the null law, which states that 0 ANDed with anything is 0, and also that 1 ORed with anything is 1. We then have the idempotent law, which states that anything ANDed to itself is itself, and that anything ORed to itself is also itself. And then we have the inverse law, which states that anything ANDed to its inverse is false, and that anything ORed to its inverse is true. And logically this follows because for the AND form, a statement cannot be both true and false, and for the OR form, a statement must be true or false. Next we have the commutative law, which states that the order of the arguments doesn't matter. A ANDed to B is equal to B ANDed to A, and A ORed to B is equal to B ORed to A. And then we have the associative law, which states that the grouping of the arguments doesn't matter. The quantity A ANDed to B ANDed to C is equal to A ANDed to the quantity B ANDed to C. And for the OR form, the quantity A or B ORed to C is equal to A OR to the quantity B or C. The next few rules are where things diverge a bit. You have the Boolean algebra version of the distributive property. The OR version should look familiar from algebra. Multiplication, or AND in our case, distributes over both sides of an addition, or an OR in our case, inside parentheses. Logically, this makes sense. If A were false, this whole statement would be false, so we need to AND both sides of this OR operation with A. A being false renders both B and C irrelevant, and the OR's result would be false. A being true just renders the statement equivalent to B ORed to C. The AND version will look strange though. In standard math, additions don't distribute into multiplications, but in Boolean algebra they do. If A were true, this whole statement would be true, so we need to OR both sides of the AND operation with A. A being true renders both B and C irrelevant, and the AND's result would be true. A being false just renders the statement equivalent to B ANDed to C. Next is the absorption law. It defines situations where values are made irrelevant. If A were false, this whole statement is false, but if A were true, true is being ANDed to true or to B, so the OR would be true, making the AND true. B's value doesn't matter. The same goes for the OR version. A being true makes the whole statement true, but A being false means this AND can never be true, thus the whole statement is false. B again doesn't matter. And finally, the big one, De Morgan's law. De Morgan's law establishes that there is an intrinsic relationship between the and OR operations. Not and is equivalent to an or with the inputs inverted, and this makes sense if said aloud. If A and B are not both true, then at least one of them is false. It also follows that not or is equivalent to an and with the inputs inverted. If neither A nor B is true, then A and B must be false. You can actually see these in the switch equivalent circuits. The NAND gate looks an awful lot like the OR gate, and the NOR gate looks an awful lot like the AND gate. De Morgan's law means we can construct an AND gate from an OR gate and vice versa if we invert the inputs and outputs. This has some interesting implications. Let's say you have a device which performs a NAND or NOR operation. If you tie the inputs together, following the idempotent law, the internal operation collapses to just not A. Since we can turn NAND and NOR gates into NOT gates, this means that all types of logic operations can be performed from collections of NAND or NOR gates. And there's actually precedent for this. The entire Apollo guidance computer had only one type of logic gate, the 3-input NOR gate. It was built from around 2800 dual 3-input NOR gate ICs. We can convert the OR relay circuit from earlier into a NAND circuit by simply inverting the inputs. All we have to do is move the poles of the relay from the normally open position to the normally closed position. This means that the LED will get power from either relay until both of them are turned on, or in our case both buttons are pressed, and this forms the NAND gate. If I push either button, the LED stays on, but if I push both buttons, the LED turns off. And we can convert this back into a NOR gate by simply putting the contacts in series rather than parallel. Now when I connect power, the LED turns on, but if I push either button, the connection is severed, and the LED turns off. Let's look at the last core logic gate type, the exclusive OR. An XOR gate's output is true when either A or B is true, but not when both are true. XOR is defined as the quantity A and not B, or the quantity not A and B. As there are three AND OR operations happening here, we need to use both poles of the relays. The normally open contact on one side is connected to the normally closed contact on the other. One relay must be energized to complete the circuit, but if the other is energized, the circuit is broken again. Let's modify the NOR gate from earlier into an XOR gate. We're first going to connect the second pole of each relay in series, And as the current pole is connected to the normally closed side, we'll connect the normally open side of the second pole to power. After the second relay, we'll connect the normally closed side of that pole pair to the normally open side of the other pole. And after reconnecting the LED and resistor, we can power up the gate. The LED is off by default, but if I press one of the two buttons, it turns on. But if I press both buttons, it turns back off. Another fun way to think about XOR is that it's a programmable inverter. So if I just push one, it's a buffer. If I hold one in, then it's an inverter. And finally, let's take a look at the XNOR gate. Again, you could use an inverter stage after an XOR circuit, but as practice, let's use our boolean algebra to solve for the simplified version. First, we apply the OR form of De Morgan's law, and then finally apply the AND form of De Morgan's law to each side of the resulting AND. We then cancel out the double inversion and are left with this. It's easier to map Boolean equations to relay circuits when the outer operations are ORs, but this does represent an XNOR. Remember that not A and A cannot be true at the same time, so if not A is true, not B also needs to be true for the gate to output true. But this is annoying to build a circuit for, so let's keep simplifying. Distribute not A or B into the other side and then apply the distributive law again. Cancel out A and B and not B because of the inverse law, and we're left with A and B, or not A and not B. This gives us a far easier circuit to implement. Notice that this circuit looks just like the original XOR, but one of the inputs is inverted. XNOR is equivalent to XOR with a single input inverted. So if we flip the context on just one relay, we have an XNOR gate. The LED is on if no buttons are pressed, and turns off when I press one of them, but if I press both, it comes back on. Now that we have the theory out of the way, let's figure out how we want our robot to actually work. Let's use this old Lego robot as a stand-in. So I said that this is going to be an obstacle avoiding robot. What we'll do is install a bumper on the front and the back of the robot, and essentially when it's on, it will drive forward until it hits something, and then it will reverse until it hits something again. A bit like the old hex bugs. But we can do better. Rather, we'll install what's called a triple point, or a three-way bumper onto the front of the robot. Essentially what that means is a bumper that has three distinct contact states that it can detect. Essentially a left press, a right press, or a center press. And so what we'll have the robot do is if it drives forward and it hits something in the center, it'll do what it did before, which is back up until it hits something again. However, if it presses something on the left side, we'll have the robot back up to the left, hopefully running back into whatever it hit in the first place, and then drive off. And we'll do the same thing for the right. If it runs into something on the right, it will then back up to the right until it hits something and then drive off. So this press front and press back mode lends itself very well to the set reset latches that we've been building. Essentially, the set is pressing the bumper on the front, and the reset is pressing the bumper on the back. And since we have a left and a right bumper, we'll add two more latches, a left latch and a right latch to hold the state of the bumper. And so let's actually draw a state diagram for this. So at this point, we have three latches in our design. We have the on latch, we have the L latch, and the R latch. And what we'll do is we'll produce two signals from each latch. We'll have an L signal, which equals true when the bumper is pressed. We'll have an L bar signal, which equals true when it's not pressed. We'll also do the same for the right latch. R equals true when pressed, and R bar, which equals true when not pressed. Alright, and since we only have two latches, 2 bits of state, there are only 4 distinct combinations of states that they can be in. So we can just draw a very simple state diagram. So we'll just have L bar, L, R bar, and R. So in the L bar, R bar state, the robot should go forward, since neither bumper is pressed. If the left bumper has been pressed, but the right bumper has not been pressed, it will back up to the left. And then if you have the left bumper not pressed, but the right bumper is pressed, then we'll just back up to the right. And if both bumpers were pressed, we'll just have it go backward. And so we can start drawing the schematic diagram for this. So we're going to start with the relay that we've already installed on the breadboard, which is the relay that supplies power to the circuit. It's constructed the same way our previous latches have been. There's a normally closed switch that supplies power to the coil that functions as our off switch, and then there is a normally open switch that, when pressed, will connect the coil to ground, powering up the relay, and then one of the relay's poles will latch to ground and keep the relay on, and power will be supplied via the other pole. Since we want to have the two outputs from our relays that define a pressed and not pressed signal, we're actually going to construct the bumper state latches slightly different than we have before. We're essentially going to swap the positions of these on and off switches. Basically, the normally open switch when pressed will supply the positive side of the coil. So that will look something like this. We have our poles as before. So we're going to have a connection up to the positive rail, and then we're going to go through a normally open switch to the next pole. Then that will connect to our coil. We'll call this the left relay. So this will supply L. And what we'll then do is connect this side of the coil through our two normally closed switches that represent our bumpers, which are set up in a wired OR format. So that if either the left or the right side of the bumper is pressed on the rear, the system will turn off. So these are the rear bumper, or I should say that the bumper latches will turn off. And this is our left bumper. And on this side, we'll have this connect up to our positive rail. Then these two are disconnected. And this side will supply our L bar signal. So we've connected the L bar signal to the normally closed side of the relay, so when this relay is not energized, power will flow from V on, essentially out of our power relay, out through the bar signal, indicating that L bar is active, meaning that the bumper is not pressed. If this relay triggers, essentially if the left bumper is pressed, the circuit through the coil will be completed, which will flip the state, disconnecting L bar and connecting this pole to V on, which will then power the coil until such time that the rear bumper is pressed. And we'll do the exact same thing for the right side, which will just essentially be a carbon copy of the existing latch design. These two are disconnected. There's a switch here. So the pole will come up. This will serve as our R bar signal. This will serve as our R signal. And we'll bring over the negative side of the coil through our rear switches. And just to help us define a net later, we'll call this C ground for the coil ground. And this is our right bumper. So now let's actually construct this on a breadboard. Starting with our left relay, the first thing we're going to do is connect both of our normally closed rear bumper switches in series to supply the negative side of the latch coils. And we'll connect that between the breadboard's negative rail and the negative side of the left latch's coil. Then we'll take one of our normally open switches to serve as our left bumper and connect it between the positive side of the left latch's coil and the positive side of the breadboard. Remember that the breadboard's positive rail is the V-on rail from the schematic. We'll then connect the relay's pole to the positive side of the coil, and then connect the normally open side of that pole to the breadboard's positive rail. And just to verify that this latch works, we'll connect a resistor between the other pole's normally open side and the negative rail, then connect the LED through that pole to the positive rail. And now when we connect power, we first have to switch the system on with the on button, and then we can turn the LED on and off with the left bumper switch and either of the rear bumper switches. Now let's set up the right bumper latch. First, we're going to replace the resistor that was on the normally open side of the pole with a wire to the positive rail on the normally closed side of the pole to form the L-bar/not L signal. We'll also remember to remove the LED. And we're basically going to set the right bumper latch up identically as the left bumper latch, although we'll connect the negative side of its coil to the negative side of the left bumper's latch coil. And then we'll add another normally open switch to serve as the right bumper. And just to test that this setup works as expected, we'll just set up some LEDs connected to the L-bar and R-bar signals. Now after powering up the circuit, both LEDs turn on because they're both indicating the bumper not pressed signals. Pressing the left and right bumper switches turns off its corresponding LED, and pressing either of the rear bumpers resets both LEDs back to on. So now that we have these L-bar, L-R-bar, and R signals, how do we actually use these to control motors? Well, we should first probably talk about how we actually drive motors. So for brushed DC motors, such as the ones we're going to use in our robot, whenever the coil is connected one way, the motor will spin one direction, and if you connect the motor in the opposite direction, the motor will spin the other way. And we'll call this forward and backward. Alright, so we need to define a state mapping between the actions on the state diagram to the way the motors are connected. So let's call the sides of the motor A and B. And then we'll define a motor L for the left motor, and a motor R for the right motor, and those will need the signals MLA, MLB, and then MRA, and MRB. So to map the state diagram onto the pins of the motors, let's define which way the motor's pins are connected in each of these states. So we'll first start with the forward state. And so for MLA, since we want it to go forward, we'll need it to be connected to on. And for MLB, we're going to say it's connected to ground or negative. And for MRA, since it's moving forward, it's also going to be connected to on, and MLB is negative or ground. So just to copy over the grid labels, this is the L-bar column, and this is the R-bar row. And so in the next state, which is our back left, we want the motor to stop and the right motor to reverse, so that the robot will spin backwards to the left. Since the left motor is stopped, we want MLA equal to ground, and MLB also equals ground. Although no connection is also perfectly suitable here to turn it off. And then MRA should be equal. Since we want it to reverse, we need to flip these pins. So this should be ground so that it goes backwards, and MRB will be connected to on. This on signal being the same as the V-on signal. And then this is going to be our L column, and then this is our R row. And then for back right, it's basically the same thing as back left, except we flip the motors. The left motor will reverse and the right motor will stop. So MLA equals off, or is connected to ground. MLB equals on, to reverse the motor. MRA is equal to ground, or no connection. And MRB is also equal to ground, or no connection. And finally, for the backward state, both motors are spinning in reverse. So we'll have MLA equals ground, MLB equals on, MRA equals ground, and MRB equals on. And so, to try to look for some patterns in this, let's convert these into binary equations. So let's look for states for which each of these signals are true, or on. Let's start with MLA. So for the forward state, it's on, and it to L bar, and it to R bar. And so if these signals are true, then this signal MLA is on. However, in none of the other states is the MLA signal on. So this is the only scenario in which MLA is true. So now we'll define MLB. The first scenario in which MLB is on is this L bar R state. The MLB signal in R bar L bar is ground. On L R bar it's off. However, in L bar R it's on. So we'll do on, and it to L bar, and it to R. And now let's define the MRA signal. So MRA is on in L bar, R bar, and like MLA, it's also ground in every other scenario. So it's on, and it to L bar, and it to R bar. So, and then MRB is on in L R bar, so on, and it to L, and it to R bar. Oh, I forgot the second part of MLB. Okay, so MLB is also true when on, and it to L, and it to R. And then MRB is on in LR bar and LR. So on, and it to L, and it to R. So in these equations, given our Boolean algebra simplification rules, we know that given the distributive property, this equation is equal to on, and it to R, and it to the quantity L bar or to L. And given the inverse law, L bar or L is true, so we can just cancel out L bar and L. So in this case, all these can be simplified. Same thing down here, R bar and R. These can all be simplified to, this is true when on and it to L. This is true when on and it to L bar and it to R bar. This is true when on and it to R. This is true when on and it to L bar and it to R bar. So in order to map these signals onto the motors, notice that on the ML signals, some statement is based on R being true, and the other one is based on R being false. And on the MR side, we have the same pattern with L being false on one and L being true on the other. Because of these signals, it makes me think that this might map well to a circuit called a multiplexer. And so what a multiplexer does is it selects one of a collection of input signals based on a separate selection signal. So we're going to talk about the 2-to-1 mux. So there will be 2 inputs and 1 output because it takes 2 signals and selects one of them to output. One side is the 0 input, and the other side is the 1 input. And then we have the select signal. So taking these ML signals, for instance, let's define MLA as if it was on one of these multiplexers. If we say that the R signal is our selection function, and we're outputting, say, MLA, If R is 0, we want it to be tied to the L bar signal. And if R is positive, if R bar is false because R is true, then we want ground because we can only be true if R is false. So if R is true, we need to map it to ground. If R is false, we can map it to L bar. And L bar, due to the way that our circuit works, is already ANDed to the on signal, so we don't have to worry about that. So now let's draw another multiplexer for the MLB signal. We're also going to use the R signal as our selector. We have a 0 input and a 1 input. This will drive MLB. So if R is true, we want to map it to on, essentially, and if R is false, we want to map it to ground, because this can only be true if R is true. So notice that we have a single selection function, R, and then we have two inputs on each of them. What does this look like to you? Well, if we go back to our schematic, this looks an awful lot like our relays. Essentially, there is one signal that controls the selection device to choose some set of inputs. So consider the normally closed input of the relay to be the 0 input, and the normally open side of the relay to be the 1 input, and the selection device to be whether the coil is energized or not. And because we're using two multiplexers, there are two poles, and since we use the same selection function, we can map this to a double pole, double throw relay. So let's translate this onto the schematic. So we're going to add a relay. This will be for the ML multiplexer. So we're going to have our poles as we did before. We have our coil. We'll have this go to ground as we did before. And then what this will do is go to the R signal. And then ML will be driven off of the poles of the relay. And so for our 0 input on the A side, we'll call this the A and the B side. So on our A side, for the 0 input, we'll connect this to L bar, this signal, and then we'll connect the other side to ground. And then on the MLB signal, 0, the normally closed, also connects to ground. And the 1 input, or the normally open side, will just connect up to on. And then we can just do the exact same thing for the right-hand motor. We just have to flip which signals we're using. So we can define this as a relay as well. The center two still go to ground, because they also choose... Actually, let me just make sure I didn't get this backwards. So here, if L is false, it goes to R bar. And if L is true, it'll go, yeah, so we can still tie these center ones to ground. So we'll do the coil, connect these, and this signal will go to R bar. This goes to L, and then MR is driven off of these poles. And then this goes up to on. So now let's build this on the breadboard. Alright, so let's start by removing the LEDs we were using to test the bumper latches. So first, we're going to add the relay that'll be used for the left motor multiplexers. Connect the negative side of the coil to ground, and then connect the L signal to the positive side of the coil. Then we'll do the same for the right motor multiplexer relay. Add the relay, tie the negative side of the coil to ground, and then connect the R signal to the positive side of the coil. And now we're going to add some LEDs to indicate the polarity of the motor's outputs. Each vertical pair consists of two LEDs reversed biased against each other. Depending on the polarity, only one LED will light up. And we'll have two pairs, one for each motor. And now we need to connect the multiplexer inputs. Connect the normally open side of one pole of the left motor multiplexer relay to the breadboard's positive rail. Then connect the normally open side of the other pole to the negative rail. These essentially form the reverse function. Then connect the normally closed side of the first pole to the negative rail. Then make the same connections for the right motor multiplexer relay. Connect the final input, the normally closed side of the second pole, of the left motor multiplexer relay to the R bar signal, and then connect the same pole of the right motor multiplexer relay to the L bar signal, and then finally make sure the relays are seated properly. Then connect power and press the on button. Now when we press a bumper, one of the motors turns off, and the other switches direction. and if we press the rear bumpers, they should revert to forward. Uh-oh. That's not right. Wait, the rear bumpers work if both bumpers were pressed. That's really weird. Alright, so there's a bug in this circuit. Let's go back to the schematic. Can you see the bug? I'll be honest, it took me a bit to figure out. I'll give you a hint. Unless a bumper latch is energized, the coil is electrically isolated from the positive rail. I want you to think for a minute. The intended path to ground for the latch relay's coils goes through the rear bumper switches. What happens when that path to ground is severed? Do you see the other one? Let's say the right bumper latch is powered, but the left bumper latch is not. This is disconnected. Power can only come in via the left bumper switch or the relay being closed. So this is disconnected, and this is floating. If I disconnect this switch, the current can flow through the coil, out through here, and rather than going through the rear switches, goes backward through the other latch's coil, out the L signal, then through the right motor multiplexer's coil to ground. However, if you were to have turned the other latch on, now there's no potential across that coil, so when you press the rear bumpers, the latches will power down. And the fix is, rather than having the multiplexer relay coils go directly to ground, we'll have them go through the coil ground signal, out through the rear bumper switches. Note, I made a small recording error. Only the coil's ground should go through the rear switches. The pulse should have been left connected to the actual negative rail. Otherwise, the motors would lose power when you pressed the bumper. Alright, so let's quickly go back to the breadboard and change the multiplexer relay's coils to go through the rear bumper switches, rather than the negative rail. We only just need to replace these two jumpers. And so now, if we power things up, if we only press one bumper, motors revert to forward when the rear bumper is pressed. And if we press both bumpers, it also reverts to forward. Exactly as we intended. Now it's time to make this permanent. Alright, so I've gone and converted the schematic into a wiring diagram for soldering a protoboard, so let's grab some relays and a protoboard. Honestly, I feel like using an old Radio Shack branded protoboard is fitting for a project using century-old technology, so let's flux this up and get to work. Well, I made this wiring diagram wrong. Not only did I flip the poles around, I flipped the normally open versus the normally closed sides around too, darn it. Well, let's fix the schematic and fix the board. Oh, alright. The next stage of the build was 3D modeling and printing some components I needed. I designed this neat triple point bumper based on S-springs printed in PETG. I also modeled up a case for the electronics and then printed them out on my P1S along with some other fixtures like this battery mount and an Insta360 mount. Then I pulled the soldering iron back out to put all the threaded inserts into the case, and after inserting the logic board, the case top is attached via some M3 bolts, and then the case mounts to the chassis via some M2.5 bolts that go into threaded inserts on the back. I then assembled the bumpers by installing 2 of the limit switches and then screwing on the bumper/spring assembly with some M2.5 bolts. We then attach the front bumper and the rear bumper to the frame using, again, M3 bolts, and then we can turn it on for a little functionality test. Here's a close-up on the triple point bumper. You can press the right side, you can press the left side, and if you press in the center, both switches are triggered. So now I'll put the final few threaded inserts into the battery mount, which then mounts to the bottom of the chassis using 4 M3 bolts. I'll then mount the power on and off switches using double-sided tape because I ran out of M2.5 bolts, and then finally we can sling the battery under the robot using Velcro attached to the mount and the battery. We can now do some functionality testing. Cool, it powered up without exploding, that's a win. And the on and off function seems to work correctly. So if we take a look from the back of the robot, we can see that the relays are actually actuating based on the switch inputs. And without further ado, here's the Insta360 footage of the relay bot clumsily rampaging around and being a general menace to things in my office. And here's the collection of footage taken from my phone as I followed it around the office. And that's the end of the Insta360 mount. So I hope you had fun watching my shenanigans of building something fun out of relay logic. If you have any questions or comments, please leave them down below, and come by again to check out the next episode of Bare Metal 386 when I finally get it out, or one of my streams on messing around with microcontrollers. Thanks for watching.